Okay, so we'll go ahead and take a look at what's going to be on your 4th unit exam. In my opinion, this actually is not as difficult an exam as your other 3 unit exams. There are only 3 chapters instead of 4. There aren't as many questions, so we'll see what you think. But white dwarfs, actually, they can only have a certain mass. They max out at 1.4 solar masses. If they're more massive than that, actually, electron degeneracy isn't going to support them, and they kind of something would have to give. But the volume of a white dwarf might be a little bit seem a little bit backwards, but the larger the mass of a white dwarf, actually that mass makes the volume smaller. It's a gravity thing. Nova events, I went ahead and drew a little picture up there. Actually, nova occur when we have a binary system between a retired white dwarf and actually still a beating red giant. And the red giant is swollen and actually can dump some of its fresh hydrogen onto the retired white dwarf star. And what happens with the nova event then is that actually in the accretion disk around the retired white dwarf, nuclear fusion suddenly occurs, and kind of the accretion disk kind of we have a little explosive event. And one thing about nova is that even though there's an explosion associated with it, it can reoccur because the white dwarf remains intact. Pulsars, scientists now know that actually they're a blip, 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 and this little energetic blips of energy actually are coming from a neutron star as it's rotating quickly. So pulsars are an indication of a neutron star. There are 2 types of supernova events, and in this unit we talked about supernova type 1A. And I said see above because the conditions for a nova actually are the same for a supernova type 1A. But the difference here, and I'm kind of summarizing here, is that with the supernova 1A, the material, it actually dumps onto the white dwarf itself to the point of nuclear fusion beginning in the core. I think it's in the core, or maybe it's on the kind of the outside of the white dwarf. And so this nuclear fusion event on the white dwarf itself, or within the white dwarf, actually blows up the white dwarf. So it comes out of retirement and blows up. The type 2 supernova then are something that we talked about in the last unit of material, where a massive star, more than 8 solar masses, actually tries to, it has fused silicon to form iron in its core, and it cannot fuse iron. So basically the core kind of abruptly stiffens, and we have kind of a collapse and rebound sort of situation, and it blows up, and what's left behind, remember, is a neutron star or a black hole. Gravitational redshift, I brought in a figure from your textbook, and here we have gravitational redshift occurs because something dense, and that little blue orb is either a neutron star or a white dwarf. Something dense is making a kind of little dimple in the fabric of space and time. And so gravitational redshift is being shown here by that lantern. The closer the lantern is to that dense object, the more actually kind of the bending in the fabric of space and time kind of creates a well that the light has to climb out of if that light wants to get to the observer. So the closer that light is to the white dwarf / neutron star, then the more it has to use some of its energy to climb out to reach the observer. So we see the most gravitational redshift when the lantern is close to the white dwarf, and the least amount of gravitational redshift when it's farther away from the white dwarf or the neutron star. So we talked about Einstein's general theories and Einstein's theories and his general theory of relativity. I just want you to know the outcomes. So remember that actually we ended up talking about different frames of reference, and specifically if we have somebody in a frame of reference that's moving very quickly and somebody in a frame of reference that is stationary, and things are affected. Those things are length and time and mass. So I think what would work well for your test is if you consider You are stationary, okay, and then somebody is moving in a frame of reference that's moving very fast. To that person, nothing's changed, but to you, from your reference, actually, you can see changes, and you can see the length shorten for that in that frame of reference that's moving fast. You can see time slow down, okay, and you can also see mass increase. Black holes. So, drawing a little picture of a black hole, we have a singularity in the center, and the dots actually is the event horizon. From the singularity to the outside of the event horizon is called the Schwarzschild radius. And then with regard to escape velocity, if you are inside, closer to the point of singularity, inside the event horizon, your escape velocity is faster than the speed of light. And nothing can go faster than the speed of light, so you're not escaping. Alright, on to the next chapter about the Milky Way. Milky Way galaxy. So there's a figure from your textbook, and you want to generally know the anatomy. The red check marks are the anatomy, so generally know the Milky Way has a disk component, it has a halo component outside the disk. In the center is the bulge, the Milky Way's bulge, and actually in the next chapter we talked about galaxies in general, and these are kind of features of any sort of spiral or barred spiral. Then the other thing is you want to generally know distances. So the diameter of the Milky Way is 100,000 light years side to side, and we are about 27,000 light years from the center of our galaxy out. And out at the edge of our galaxy where it's thinner, it's about 1,000 light years. And then here is a figure from your textbook that shows the stars. The stars that are in the disk are kind of indicated by those yellow lines, and I know they kind of bob up and down from the disk, but they're pretty orderly. So disk stars orbit orderly in general, and then those green lines are showing you how halo stars go around our galactic center. So halo stars are a little more random. And then, don't know if you remember this, we said if we're looking at our Milky Way, looking basically into the disk of our galaxy, what's helpful is to look in different wavelengths. And I'm not sure I emphasized this as much as I should have in lecture, but the reason we, and by the way, these little slivers are looking at the longest wavelength on the top radio wavelength to the shortest wavelength gamma rays on bottom. So we do that. We look at that in those different wavelengths, so we can actually, that energy can penetrate the gas and dust that is in our disk. So, okay, I brought in a figure for the next two, actually. So this figure is kind of hard to read, so you might want to find it in your lecture notes. But when we talk about the disk and the halo region of our galaxy, and the same thing with other galaxies, the disk part of our galaxy, we have kind of an assortment of ages, but we definitely have some newer stars being born. In the halo region, we have older stars. Not only that, but in the disk region where we have stars being born, okay, they're being born and they're living their lives and they're dying. And then remember we talked about how actually material can be given back to new stars to be made out of old stars. And so that recycling kind of builds up what we call the heavy elements or heavy metals. So in our disk we have, relatively speaking, kind of stars are what we call metal rich. And in the halo, basically they're kind of frozen in time. So they, not much recycling going on up there. They're older stars, and they are what we call metal poor. So kind of related to that, we have these terms, population 2 stars and population 1 stars. And this is one of the things in physical science that seems a little bit backwards, because population 2 stars are actually your grandparents, and population 1 stars are you. So population 2 stars are the old stars. They would be the metal poor stars located in the halo, and population 1 would be the younger stars located in the disk. Sagittarius A star, that actually is the supermassive black hole in the center of the Milky Way galaxy. And in orange here I say, why did they go with the term Sagittarius? Because you're probably familiar, that's a constellation of stars. And that's because if you want to see the center of our galaxy, what you do is you look at the constellation Sagittarius. And I go on to say that if you can find the asterism, the teapot, the teapot is such that it kind of has a spout. And so there's like steam coming up out of the spout. And in that area is Sagittarius A star. So instead of hole, it should be, of course, how. How do we know that there's a black hole in the center of our galaxy? And I'm thinking it was 15 or 19 years, folks, scientists, using wavelengths so they could penetrate, that light could penetrate, looking at wavelengths that penetrated the dust in our galaxy, they watched stars orbit this Sagittarius A star. And by how quickly or how they orbited this object, they could tell the mass of this object was 4 million times the mass of our sun, and it was confined to a particular volume that they know that its density must be that of a black hole. So for chapter 16, I went ahead and split it up onto 2 pages just to have a little extra room. Now I know with regard to galaxies, there's more flavors than just spirals, barred spirals, and ellipticals, but I kind of went with those as the 3 main types of galaxies simply because I like them best. No, I kind of threw out irregulars and lenticulars just because I think this is neat because this is actually on Hubble's tuning fork diagram. So not only be able to list them, but be able to kind of describe them a little bit for your test. And then with regard to spirals and barred spirals, the thickness of the nuclear bulge actually it's helpful. They know that however correlates well or is affected by how tightly wound the arms are. So it kind of makes sense if you stand up and you put your arms out and those are the spiral arms of a galaxy, and kind of where your body is, that's your nuclear bulge. So the more tightly wound the spiral arms, kind of the thicker the bulge. So one of the things that amazes me in astronomy is it hasn't been that long since we understood kind of the concept of a galaxy. And so Edwin Hubble, when studying the Andromeda object, didn't know at the time whether that object was just kind of a nebula or whether that object was its own galaxy of stars. And so what he did was he actually looked at a Cepheid variable star in what we now know. He looked at the Cepheid variable star in what we now know is the Andromeda galaxy. So this little star in a distant galaxy, and he looked for its period, and then knowing its period, then he could backtrack to what its luminosity was, and then he could compare its luminosity to its brightness and get to distance. So basically he used the Cepheid variable in the Andromeda galaxy as a standard candle. Pretty darn cool. And in doing so, he saw that, is it 230 million light years, I want to say, is how far away the Andromeda galaxy is. So hey, that must be its own little island of stars called a galaxy. So this one right here is basically reminding us, and we've been talking about this clear back from Unit 1, the fact that it takes light. I know it seems like when you turn on the light bulb, light gets to you immediately, but it takes light a certain amount of time to travel through space. And then because of that, then, when we look at objects that are like, hundreds of thousands of millions of light years away, we actually are seeing that object as it was 100,000 years ago. Okay. Standard candles. I mentioned a minute ago that actually Edwin Hubble used Cepheid variables as a standard candle. So standard candles, the word standard in standard candles means that we know how much energy or luminosity that an object is pumping out. We know the luminosity or how much energy an object is pumping out per second. So we can use that, compare it to what it really looks like to know how the light is diluted by distance, basically. And so we can go back and plug it in and do a little math problem to get to distance. All right, the last page, chapter 16. So Hubble, I'm going to draw the little scatter plot. What he did actually was to prepare a scatter plot of different galaxies. So these dots are galaxies, and what he did was he looked at the redshift, and using the redshift, he got to recessional velocity, so he could say how fast things were moving away from us. And then he also plotted how close or far away that particular galaxy was. So these are galaxies moving away from us. Okay, and what he found out was that the more distant the galaxy, the faster its recessional velocity. So that is Hubble's law. And actually, you can use that to kind of, in a sense, backtrack to the original time when we were all one big happy singularity at the time of the Big Bang. And so that would be about 13 to 15 billion years ago. That is the estimated age of the Earth from Hubble's law, using Hubble's constant. Related to Hubble's law, basically the recessional motion, which is recessional, like if somebody's having a wedding and they talk about their recessional, okay, they're talking about when they leave after they're married. So recessional motion is that going away sort of motion all galaxies have, most galaxies have, from each other, and that motion increases with distance, and kind of actually directly related to that, what Hubble saw was that the redshift increases with distance too. So when it comes to understanding how galaxies evolve or change over time, a tool that scientists use is to look, the farther back we look, we're looking at objects as they were babies. So basically, you can look at a far away distant galaxy and understand that that's a baby picture, and then your closer galaxies are your more mature galaxies. Your closer galaxies are pictures of your more mature galaxies. So kind of in between, you get kind of a spread of ages of galaxies. So speaking of baby galaxies, proto-galactic cloud is basically a cloud of what was available at the time of the Big Bang, hydrogen and helium. That cloud is ultimately going to become a galaxy of stars. So one of the things, and it's still happening today, galaxies are interacting with one another. But early on, galaxies were much more likely to, when I say interact, that means like galaxies run into each other or gravitationally kind of pull at each other. And the reason for that is because galaxies were closer together. The last two terms go together. Quasar event, we now know this very energetic event that occurs over kind of a wide range of energies. We now know that is associated with the centers of galaxies and the supermassive black hole in the centers of galaxies. Specifically, that energy is coming from, as I understand it, we've talked about kind of accretion disks, and it's kind of like that. Matter that actually is kind of in queue to fall down the black hole in the center of a galaxy. Now remember that sometimes students will ask me, well, how can we have this jet of energy called a quasar coming from a black hole? I didn't think anything could get past, get outside of a black hole because of the escape velocity issue. And actually this energy is on this side of the event horizon. So it's created in the accretion created by the commotion that's created by a black hole. And it is outside the event horizon. So during a quasar event, we generally say that, or quasars are associated with supermassive black holes in the center of a galaxy is actually feeding. So material is falling into that supermassive black hole and creating this jet of energy as the galaxy supermassive black hole feeds.